And whether you're a high school student or if you're a university student, grad student, or in the workforce, oh man, the chat is blowing up.
We're at 4,900 people in the chat.
And for those tuning in, again, you can watch on YouTube. We've sent out the link in Discord, so you should have access to that as well. Amazing. Okay, we will get started. To kick this off, I want to welcome you to this Coding School's Qubit by Qubit Introduction to Quantum Computing course with IBM Quantum. My name is Kira Peltz. My pronouns are she, her, hers, and I am the executive director of the Qubit by Qubit initiative and the founder of the Coding School. We are so excited to bring you here today. We initially were going to start off with 5,000 students. We received such an overwhelming number of incredible applications that we extended the course to 7,500 students. We have high school students from around the world who are receiving course credit for taking this course. We have Army veterans, we have VPs of large banks, we have product managers at large tech companies. Basically, we have people coming from all walks of life with the same common mission of learning about quantum computing. So without further ado, I'm going to turn it over to Abe, who is the lead of IBM's quantum education team, who will kick us off.
Thank you, Kira. It's really exciting to see so many people joining this conversation. I'm seeing 5,000 participants in the chat, which is it's an impressive thing to be seeing in the field of quantum computing. So hello, everyone. As Kira mentioned, my name is Abe Asfa, and I work at IBM Quantum. In particular, I focus on our quantum education efforts. I think as a first day today, a really exciting thing to do is to just kind of give you an idea of the landscape of the technology and to see how far the technology has come and why it's a really great time for you to be learning about quantum computing. And so as we put this together with the coding school, why we're motivated is really because the technology has come to a point where you can participate, where you can contribute to the field, and also really start thinking about the problems in the field that several of you will be seeing, and also maybe even showing us that are new to the field. So to give you an overview of all of this and the progress in the technology, it's really an honor to have Jay Gambetta here. So Jay, just by way of introduction, is an IBM fellow, which is a really prestigious honor to receive at IBM in recognition of all the impact he's made for the field of quantum computing, and also the vice president of the quantum computing effort at IBM. Jay is here to tell us a little bit about how far he's seen the technology progressing and why it's a really good idea for you to be learning about quantum computing. So I'll just turn it over to Jay now. And Jay, are you able to hear us?
Yes, I can. Can you guys hear me?
Okay. Yes, excellent.
Oh, first I want to thank Abe, Kira, Amir, and Fran for inviting me here. And also, wow, 5,000 people. That's pretty cool that there's this many people interested in quantum. So as Abe said, I'm responsible for IBM Quantum, and I was asked to give a few words. The organizers asked me to give a bit about me and how I got into the field, and then where I see the field going. So I'll just go through that. So where I am, so I actually grew up in Australia, and I always liked math, and so I found my way into quantum. I would say it was the area at university I didn't understand the most, so I just kept questioning things. So, like, to show a bit of history and to show how diverse quantum is, I actually started doing laser science, and it was kind of a cross between an engineering and a science course at university. And I found that I didn't get enough physics, so I decided in my honors I would do something crazy and start shooting lasers into atoms and measuring cross sections. And doing that, I found out that I actually didn't understand the math behind it. And so it was all explained by this quantum mechanics. So what I did next was I was like, all right, I'll go do PhD in interpretations of quantum mechanics. You couldn't go as anywhere further into quantum than say, let's go back to the interpretations and argue over them. This was fun, but at the end of my PhD, I decided I like building things. So I switched back working with experiments, and that's when I joined the Yale group when I first came to the US in 2004, and I started working on superconducting qubits. Here we did a lot of things. We invented the transmon, and one of the experiments that I was really proud of, we did the first demonstration of the 2-qubit algorithm using these machines. From there, I went to Waterloo, and this was mainly driven by, after we'd done some qubit work, I really wanted to understand how we would benchmark these systems. And so I did a lot of work on developing benchmarking routines for these systems. And after that, I came back to IBM, where I'm now an IBM fellow, and as Abe said, the VP for quantum. So I hope that shows that you can take, in this field, you can take a history that can be always changing as long as you keep questioning things. So for quantum, I actually think for quantum, it's actually good to start by looking at the history of classical. So if we go back to 1936, I would say the theory for classical was basically developed by Alan Turing, where he showed that you could have this notion of making a universal machine. And then in 1947, there was a big event of basically coming up with the transistor. And so this really laid the foundations for classical. And then people started to ask the question, well, how do you actually program this? And Grace Hopper, who was actually at IBM, she was the first to actually develop a language for these. And it wasn't until basically the following year that we really, when Fortran, another project out of IBM, we really started to make math libraries that could use these. And then we go through all the personal history, computers and things like that. But basically, it wasn't until 1981 that you really started to get useful computers. And it took basically 40 years from there that we've basically done HPC. And now we can do everything like model very complex molecules and systems. And basically, we've seen how much GPUs and things like this can accelerate high performance computing. But I just wanted to go through this history to sort of show that it took a long time for us to get to a point of actually making a computer and using it for complicated situations. And now these computers basically are hitting a wall. The very problem that they're trying to do, like simulate these complex molecules, these are the problems that are very hard for them to do. And I think this is what made quantum launch, right? And Feynman in 1982 basically said, look, nature isn't classical. So if you want to actually simulate nature, you better make a quantum machine. And quantum gives us that ability to simulate nature. So where are we now? I actually like to break it up into generations. I like to think that the 90s was a generation where famous people like Peter Shaw, Charlie Bennett really proved and generated the foundational theory for quantum. And so for those 10 years, this was about showing things like a quantum computer can not only simulate nature, but it can actually do other mathematical problems. And one of them happens to be breaking encryption. Others happen to be searching databases and things like this. But the math really got established that it could do something more than could be done classically. It also got established that it was possible to do error correction in these. So the theory, the 90s was 10 years of developing a lot of great theory that set the foundation. Then the 2000s, as I said, this is when I got into the field. It was really about beating our head against the wall to make a single qubit and demonstrate 2-qubit gates. So if, the first transmon was actually, the first superconducting qubit was actually demonstrated in 1999, and that was done in NEC. And it took basically that whole 10 years until 2007 when the transmon came, that was just about coming up with a better qubit. How do you actually make a quantum system that has 2 levels, doesn't experience noise, you can do operations on it, and then you can actually start to entangle 2 of those qubits together. So I like to say that 2000s was about banging our head to make a single qubit and demonstrate gates. And then what happened in 2010s? So this is really, I think, where we started to prove that multi-qubit systems could be done and we could start scaling these systems. So it was about showing that you could start to build a technology that can make bigger systems. It was also in this generation that we actually, with my colleague Jerry Chow, we had the crazy idea, could we take our research and put it in the cloud? And this was how we came up with the IBM Quantum Experience. It was a bit of the history that I think I underestimated how difficult it was, but that was what I remember that being one of the most rewarding projects, because it really showed us how to think about these systems from a system view and think about making them bigger and more stable. And since then, we've put multiple systems online. I'm sure you guys have used them and seen them. Also in this generation, after we put one on, it was where we started to say, well, how should we program these systems? And there are many different people, many different contributions to programming, but it started to answer the question, what would a compiler for a quantum computer would be? And I would say that question is not answered fully yet, but it was the start of actually starting to program them. So what do I see the 2020s? Well, actually, I think it's going to be the most exciting generation. I think in this generation, we'll truly see quantum advantage. If you guys have seen, we put our roadmap from us, what we think the hardware we can do to scale these systems well beyond what you can actually simulate with a standard computer. But more importantly, we need to keep understanding this math, work out what we can do with it. We need to develop better and more efficient codes. And we need to come up with how we are actually going to program it. We need to build those math libraries, which I talked about happen with the likes of Grace Hopper and Fortran. We've got to do the same for quantum. And we really are just at the beginning. So if I was to look back, and one thing I hope that can happen is, I hope it doesn't take 50 years, as it happened with classical computers, to get us from something where we start, well, actually 70 years from we start demonstrating math libraries to where we are today. I hope we can do it in 10 years. And to me, and the reason why I drove so hard with the IBM Quantum team that we want to do things like this, work with the community, is I believe it's only possible if we do it together. So it's my understanding in semester 1, you're going to learn about the math. Semester 2, you're going to start programming algorithms. And I think I'll conclude and welcome you to the school. And I wish you the best, and I'm looking forward to see what you do. Thanks.
That's awesome to hear this, Jay. Thank you. And before we let you go and really just start recognizing the work that goes into these quantum computers, I'm seeing one question from the audience about what backgrounds are useful for studying quantum computing. Do you have an answer to this question?
Yeah, I get asked this all the time. Honestly, the best background to have is the background to answer questions. So quantum is a field that is spread over so many fields. I work with chemists, I work with engineers, I work with math, I work with physicists. Everyone contributes. So the things that you need to have a grounding in linear algebra, and I think you're going to go through this in these courses. And you need to then be able to have an open mind to take the knowledge of the different domains and see where that linear algebra goes. I would say quantum, the math is reasonably simple. The implementation in the math and what the math applies for what you do is where it starts to get complex. And this is where some experience from different domains. So I didn't really answer your question, but get some linear algebra math and then be open to trying many different areas.
Yeah, thank you, Jay. Really highlights the interdisciplinariness of the field and how everyone is welcome to make contributions with just the right backgrounds. All right, with that note, we'll thank Jay for his time. It's really an honor to have you here, Jay. Thank you. And we'll pass it back to Kira and the team.
Thanks.
Thank you, Jay, and thank you, Abe, so much, both for parting kind of your words of wisdom, and especially as we have 7,500 students starting their quantum journeys or continuing their quantum journeys. We are also so excited to see what all of our students are able to do. And furthermore, we want to thank IBM Quantum for making this possible, for making it accessible and free. This would not have been possible on the scale that we are doing it now, and to reach so many students as it is from with IBM Quantum support and collaboration. So thank you again. And then without further ado, we're going to get started. I want to kick off with some just course logistics. And these are reminders. You all should have watched the orientation video, but we're still getting a series of questions related. So we just want to make sure that we're going through this. So I'll cover this quickly, and then I'll pass it over to Amir, who will get us started on our lecture for today. So I want to remind all of you, we do have a code of conduct. It is the utmost importance to us that our community remains inclusive and that everyone feels safe so they can do their best learning. Please make sure you are adhering to the code of conduct. And if you do see something or you experience something that makes you uncomfortable or is in violation of the code of conduct, please make sure you're filling out the form, or if it's an urgent matter, you're contacting us directly. There are protocols in the handbook, but this is our top priority, is making sure you all feel safe to learn. Now, course norms. You'll hear a lot about failure and an uncertainty in this course. We think it's incredibly exciting that the field of quantum computing has not yet been fully written, and all of you have the opportunity to contribute to this field. With that said, that means that there's going to be a lot of uncertainty and a lot of failures along the way. Most of you, and many of you in high school, have been taught that the sciences, there's a right and there's a wrong answer. I want to make sure that you're aware that there are still questions in quantum that have not been answered. And so we want you to sit well with uncertainty. And for us, curiosity, effort, engagement, those are going to be valued in the course over perfection. So we want to make sure you're not stressed out about grades, you're not stressed out about the course content. As long as you're willing to learn and have an open mind, that's all we can ask from you. So there are three main components to this course on a weekly basis. There's the lecture, which you all are attending right now. And yes, there will be recordings available for, I know it is late and some of you are staying up right now. Recordings will be available. Also, subtitles will be available on the recordings. So don't worry about that. There will be subtitles that you can follow along with on the recordings. The lectures will be at this time every week. The Zoom link is the same Zoom link you will use on a weekly basis. There is also a lab. For those that were confirmed before Saturday, you should have received information about the lab. Gabby will also be, well, not for the lab, but we will be sending out more information on the labs for anyone that confirmed on Saturday or today. But there will be a lab. They do start this week. They'll be between Tuesday and Saturday. There will be different labs for high school students versus those that are in university and the workforce. There will also be recordings if you are unable to make the lab. So please make sure you're following the directions on the form. If you got the wrong form because you had marked you were a high school student and you're really in university or above, again, there are clear instructions on the form. And if you click the box saying you got the wrong form, you'll be sent the right one. Labs, just additionally, will largely go over what was covered in the lab and practice problems similar to what's on the homework, or problems and questions that students had in the week before. Homework, there will be weekly homework. It will start this week. You will be submitting it on Canvas, but not this week. We will be opening up Canvas next week and you will submit your homework assignments there. So this week, there will be nowhere that you will submit your homework assignments. Keep your answers and wait until next week when Canvas opens, and there will be a submission place for that. We will send over the homework at the conclusion of the lecture, and it will also be on Discord. Now, you have unlimited submissions before the deadline. So again, we're not expecting you to get everything right. And even when you do submit, we don't expect you to get everything right. This is a learning experience. And as we will note time and time again, it takes time for you to truly understand all of the concepts. So as Abe and Jay mentioned, we've broken up the material into 2 semesters. For the first semester, it will largely cover the math required for quantum mechanics and quantum computing. Many of you who are in university or above may be quite familiar with a lot of the content that is covered. So just if you feel like it's a review or it's too easy, just wait. Second semester, we're going to delve really head on into quantum mechanics, quantum information and computation, and quantum algorithms. But it is important in the first semester that everyone does have this knowledge. We also will be, as much as possible, relating the math and the concepts that are taught this semester to quantum computing. So it's not just like we're teaching a math class. We are teaching this in the framework of how this is going to be used in the field of quantum. Now, technologies. So I want to be very clear, first and foremost, what each platform is going to be used for and whether we have released it or not. So Discord. This is where we are going to communicate with you. It is our main form of communication. We will not be sending emails on a weekly basis or when there are important matters. We will be putting it in course announcements, the Discord channel. So if you have not already, signed up for Discord or gone through and been verified, after the lecture, we will be verifying individuals until I believe it is 8 p.m. Eastern time. So please make sure you do that. We will also put out more times available for the rest of this week to be verified. We've extended the deadline. Today is not the last day, but we would like to get as many people verified as soon as possible. But make sure that you have email notifications on for Discord and that you're checking it on regularly. So that's Discord. We are separating roles into students. So if you're blue, you're a student. If you're orange, you're an adult. You're a university student or above. We will be adding in more channels and more options to form community as the course goes on and as the semester goes on. But for right now, it's critical that everyone gets familiar with Discord and that everyone understands how to see communication from us. That's our top priority. And we do definitely want to make sure everyone can foster communities and socialize with one another. So just be patient, that will come. Now, Piazza, we will be opening up Piazza this week. It has not been released yet. Piazza will be where you'll ask all your academic related questions. So if you're confused on something that Amir has talked about in the lecture today, you would post it on Piazza. You should look for an email from Piazza to sign up between later today and through Tuesday. So please don't ask us about Piazza until after Tuesday if you have not gotten an email about signing up for Piazza. Canvas will not be introduced this week, but when we do introduce it, we will let everyone know in next week's lecture. This is where, it will be the central hub of all the course material. So this eventually will be where we post all the recordings. It will be where you submit your homework. It will be where you get your homework for that week. So that will largely be covered on Canvas. Again, right now, what you need to do is make sure you're on Discord and that you're checking the course announcements and the channels that, we from Qubit by Qubit post announcements. So just some key takeaways. These are common questions that we get. So Discord is your main source of communication and it is how we will communicate with you. Please make sure you're checking the official channels. If you have not already confirmed your spot in the course, do so now. If you have confirmed, you don't need to resubmit, but we have a number of people who have signed up for labs and have been accepted but did not confirm their spot. Gabby, if you could post in the chat the confirmation, that would be great. Labs will start this week. Again, if you have received the email, fill out your preference. If you got accepted, you will, if you just got accepted into the course, you'll receive this email later today about labs. Fill it out as soon as possible. It's important for us to be able to sort out what lab you're going to be in. Piazza will be introduced this week. Canvas will not be introduced this week. And homework will be released in Discord after the lecture. Friends are still able to apply. We've opened a wait list. We'll be allowing students in throughout this semester, as well as next semester, at the beginning of next semester. So there's definitely still the opportunity to apply and opportunity to be accepted into the course. This next point is very important, and I've mentioned it multiple times, and students are still not adhering to it. Do not message LinkedIn, Discord, your instructors, or TAs. This is incredibly important. Our teaching staff and academic team are very busy, and they are not able to deal or handle one-on-one conversations. They're focused on making sure the course content is as good as possible and focused on the content. So do not be reaching out to them. For administrative staff like myself, again, individual messages that refer to things that are already covered in the student handbook or that I've covered in the lecture, you do not reach out individually to us about those. Please make sure that you're asking in Discord in the channels before you reach out to one of us about a specific question. And then the last point, you are committed to completing this course through mid-May 2021. If you are going to drop, this is your last chance. I also believe that we do have an official drop form. We hope you all stay. We think this course is truly going to be incredible and you all will learn a lot, but there are plenty of students who are eager to learn, and we will give your spot to someone who can participate for the whole time if you've realized that you cannot. And with that said, I'm going to turn it over to Amir, who will get us started on what we're learning today. I have my pen and paper to start taking notes. Again, these slides will be available at the end of the lecture, so you can take notes on what you think is valuable, but you'll be able to refer back to the slides afterwards.
Hi, everyone. I'm very excited to talk to you guys about classical computing today. So we're going to talk a little bit about the history of classical computing, and then we're going to talk about binary representation. So what is this binary that is so central to everything that a computer does? And then we're going to segue into Boolean logic and potentially discuss some algorithm thinking at the very end. So with that, what you will be learning in this lecture is, first of all, what are bits? And we have talked about quantum bits, classical bits, but what are they actually, and how do we deal with them? Then we're going to talk about Boolean logic, universal computation. What does it mean for a computer to be a universal computer? And then reversible computation. So with that, let's start with a bit of history of classical computing. So first of all, before we talk about history, I just want to give you guys a definition or an image for what computation is. So computation is a mathematical calculation that maps inputs to an output based on a set of instructions. So again, if you look at it here, we have some inputs. We feed it into our computer, which does computation, and then these computations are done based on a set of instructions that are actually called algorithms, but we'll get to that later. And then based on that, our computer returns an output. Okay, so let's watch this short YouTube video. Oops. Technical difficulties. Yeah, and as you can see, there has been decades of innovation and improvement on the general idea of a computer, until we get to the devices that we use today. I mean, some could argue that again, laptops or smartphones would have been unimaginable for a computer scientist of 1940s and 1950s. But then again, we show you this history just to draw analogs for quantum computing in the future. But anyways, before we talk about quantum computing, let's talk about base representation in a computer. And the point of this section is that we want to learn to think like a computer in order to understand how a computer works. Okay, so first we're going to talk about decimals. So the decimal number system is based on numerical digits between 0 to 9. It's also referred to as base 10, and a base is something that determines the numbers that get represented and how we perform arithmetic operations. So I would say decimals are what we're used to on a daily life. It's just simple addition. And let's look at a few examples. And again, we're just going to try to see how we can write these, write things in base 10. So for example, if we have number 6, we can write that as 6 times 10 to the 0, which is just 1, which is 6. Now, if we have number 36, we can write that as 30 plus 6. Now, 30 is 3 times 10, or 10 to the 1. And then 6 is just 6 times 10 to the 0. Now, if we have 536, again, that is 500 plus 30 plus 6. And we can represent 500 as 5 times 10 to the power of 2, the 30 as 3 times 10 to the power of 1, and then the 6 as 6 times 10 to the power of 0. And the whole point of writing a number, these decimal numbers out this way, is that we basically are writing everything in the base of 10. So every digit is just an extra power of 10 in some sense. Now let's do a practice. How would I write out the number 28? How would I represent number 28 in the same form that we did for the examples? I'll give you guys roughly 20 seconds so you can write this out and work this through, and then we'll see how to do it together. And then if you're done with that early, try to write the number of 432 again in the same way as a breakdown of the different digits in base 10. Okay, so I'm going to start with the number 28.
Amir?
Yes.
Before going forward, could you just explain again why we are learning about decimals and writing out decimals in base 10? Like, how does this relate to quantum computing, or how does it not relate?
Quantum and classical computers you work in the binary basis, which is the next thing that we talk about. And the reason why we're trying to break down things this way is to be able to make sense of, how do computers actually think about these numbers. Now, human beings are used to thinking in, again, base of 10 or decimals, mostly because we have 10 fingers, and that's how math has been developed since. But we're just trying to think about the same systematic way of, how does the math work, and then extend that to how do computers think about math and these numbers and represent these numbers. Okay, so with that, 28, I can just write that as 20 plus 8, right? And 20 is 2 times 10 to the power of 1. And 8 is just 8 times 10 to the power of 0, which is 1. Now let's try the other number together. So 432, I can write that as 400 plus 30 plus 2. Now 400 is 4 times 10 to the power of 2. 30 is 3 times 10 to the power of 1. And then 2 is 2 times 10 to the power of 0. And if I give you any number in decimal, you can write it out this way. Okay, so next, let's talk about binary. So while it's common for us to use base 10 for counting, there's no mathematical reason to prefer one base over another. And computers use base 2 actually, which is the most important basis for computation. Now, base 2 is also referred to as binary, meaning that there are only 2 possible values for every digit, and that is 0 and 1. So you can think of 0 as a light switch or as a light bulb being off, and a 1 as a light bulb being on. And turns out you can, any number that you can represent, in basis 10 with the decimal basis that we're used to, you can actually represent with binary as well. And every binary digit is referred to as a bit, which again are the building blocks of our computers. Now, if you're a classical computer, you have a classical bit. If you're using a quantum computer, you have a quantum bit. But still, they only have 2 possible values that you can get out for every digit. And then all the operations in classical computers, and actually for quantum computers for that matter, happen by manipulating these bits and qubits. So how do we convert bits? So let's say I give you the number 101010 in binary. What does that mean to you? Well, we're not computers and we're used to base 10. So if you look at this number immediately, it shouldn't make any sense. So first, let's go through the same methodology that we had before. First, let's write the number 1010 or 1010 in decimal. So I can write that as, again, my base is 10. So I can write that as 1 times 10 to the third plus 0, which is the next digit, times 10 to the 2 plus 1 here, times 10 to the 1 plus, again, 0 here, times 10 to the 0. And again, if you add this up, it gives you the number, 1010. Now, what about, this number 1010 in binary? Okay, so again, this is where the difference in bases come from. So if the, let's say, if the leftmost digit in the decimal was worth 10 to the power of 3, now we're in basis 2. So this leftmost digit is actually worth 2 to the power of 3. So if I were to write this out in binary, I would have 1 times 2 to the power of 3, a 0 here times 2 to the power of 2, a 1 here again times 2 to the power of 1, and then a 0 here times 2 to the power of 0, which is 1. And then if I add these numbers together, I get 10. So 1010 in binary would be 10 in decimal. And okay, you will become more comfortable with this once we see a few more examples. So let's say we have, the number 1100 in binary, or this is the bit representation. What is this number in decimal? So I want you guys to take 30 seconds to work on that. Again, remember, so it's the same method, except for that, the value of each digit is different in binary compared to decimal. So, if you're counting if you're going from right to left, then, instead of raising the value of each digit as like 10 times, 10 to the power of like, the slot of that digit. Now it's 2 to the power of the slot of that digit. So take 30 seconds, work on this yourself, and then we'll go through an example together. Actually, both of these examples together. Okay, so let's go through the first one together right now. And again, here we're gonna point out what the difference between binary and decimal is, which is what we're used to. So let me first look at this first bit 1. What is the value? So I can write this as, oops, what did I do? Okay, so I have a 1 times, okay, so 0, 1, 2, 3 times 2 to the power of 3. That's the value of that digit. And then I have another 1 right after. And now the value of that digit is 2 to the power of 2. And then, the value of the next digit is 2 to the 1, and the value, the worth of that digit, and the value of the digit is 0. So 0 times 2 to the 1, and then plus 0 times 2 to the power of 0. And when I add this up, I have 8, which is 2 to the power of 3, plus 4, which gives me 12. So 1100 in binary is equivalent to 10 to the number 12 in the normal decimal representation that we're used to. And let's try the other number out now. Okay, so I have a 1 here. Again, we're gonna start with this digit, or that bit for that matter. So okay, 0, 1, 2, 3, 4. So that's times 2 to the power of 4. Then the bit that's worth 2 to the power of 3 is 0. So 0 times 2 to the 3. 0 times 2 to the 2. And then, okay, so we've gone through these bits so far. And then now the next bit is this 1. So that's 1 times 2 to the power of 1. And then the last one is also a 1. So 1 times 2 to the power of 0. And then when I sum this up, so 2 to the power of 4 is 16, plus I have 1 times 2 to the power of 1, which is just 2, and then plus a 1. And that gives me the number 19 in decimal. So 10011 in binary is equivalent to the number 19 in decimal.
Amir, could you explain why in the ones place we start off with 2 to the power of 0?
Well, 2 to the power of 0 is just 1. And that's in any representation, where it be binary or decimal, this very first digit, like the digit that's to the rightmost digit, has a value of like, base to the power of 0. Now, again, in binary, this base is 2. So you have 2 to the power of 0. In decimal, and there's a bit of a lag, I apologize for that. This base is 10, so that makes it 10 to the power of 0. And both of these are equal to 1. Any number raised to the power of 0 is 1.
And why do we use the number 2 as the base for binary? Is it because there's only 2 digits, 0 or 1?
Well, that's the definition of binary. So binary is base 2, And as a consequence, there are only 2 allowed digits, which are 0 and 1. Because as soon as you get a 2, you get a carry bit. And we'll see this when we do addition. But again, just to draw an analogy to the decimal system that we're all used to. If you add 2 numbers, let's say you have like 5 plus 5, then that the first digit is going to be 0 because you add up to 10 and then you get a 1 carry bit over. Now it's the same thing. So the same way that you can't have like a value of 10 at any of your digits in decimal, you can't have a value of 2 for any of your digits in binary.
Awesome. So just last thing. So we started off in my first question saying that for the ones place, it'll always be 2 raised to the power of 0. So then just to be clear, after that, in the tens place, it just goes up, correct? In counting, it goes from 2 to the power of 0 to 2 to the power of 1. Could you write out a binary has 2 digits in the like tens place as well, and just write out what that looks like?
So something like, again, I'm going to use this space here. So like, for example, if you have 11 in binary, that is 1 times 2 to the 1 plus 1 times 2 to the 0, which is 3. But again, to draw an analogy, so this is, I'm going to call this binary. And then if we have, the decimal, which I'll call D here, if I have 11 in decimal, that's going to be 1 times 10 to the 1 plus, 1 times 10 to the 0. And again, this is the difference in bases. So here, instead of in decimal, you raise, you have like your base to the power of whatever the digit position is, whereas in binary you have 2 to the power of whatever the position of your digit is. And again, this is something that, this transition is something that you guys will get more comfortable with, especially after you do the homework. It might seem a little bit or unintuitive initially, but this is something that just requires a little bit of work. Okay, and then, just for practice, this is not essential, but just so you guys would see it. Let's try to convert, a decimal number to the binary representation. So we're going to do a form of long division for this. So okay, let's say we have the number 33 here, and then I have the different powers of 2 listed here for you. So I can write the number 33 as, again, 32. Actually, I'm not even going to do the long division. There's an easier way of doing this. We can write 33, right, as 32 plus 1, correct? And that is equal to 2 to the power of 5. Again, I have this here, plus 2 to the power of 0. Now, if I were to write this in binary, then I'm going to have, I expect to have a digit that's worth 2 to the power of 5. So I'm going to put a 1 there. And then I have no digits or no values of 2 to the power of 4. So the next digit is going to be 0. Nothing with 2 to the power of 3 here. So again, another 0. Nothing with 2 to the power of 2, another 0. Nothing with 2 to the power of 1, another 0. And then again, 1 digit that's worth 2 to the power of 0 or 1, a 1. So this is how we write the number 33 in binary. Now, if you guys, want, again, another round of practice, maybe take, 30 seconds and just try to verify that this number in binary is equal to 33 in decimal using the same methodology that we talked about earlier. Okay, let's move on now. So the next thing we want to talk about is arithmetic operations for bits. Again, this is how computers compute. Now we're fairly familiar with normal arithmetic operations. So for example, addition is just summing two numbers. Now when we're adding bits, this is very similar to the normal decimal addition or the normal addition that we're used to. Except here's the one exception. So normally when we do decimal addition, or again normal addition, we have the carry bit. We get a carry bit when the sum of two numbers becomes larger than 10. But in the case of a bit or binary, we have this carry bit when the sum becomes larger than 2. So let's go through an example here. These are like the very basic numbers. So 0 plus 0 is just equal to 0, correct? Now 0 plus 1 is just 1, and 1 plus 0 is just 1 again. Now what about 1 plus 1? So if we're thinking about these numbers in the decimal world, 1 plus 1 is equal to 2. But now in the binary world, you can't have a value of 2 at any given digit. So what will happen is that you'll get a carry bit over. So 1 plus 1 becomes 1, 0. And again, all these are in binary. And just to verify, so if you want to translate this 1, 0 to decimal, then we write this as 2 to the power of 1, or rather 1 times 2 to the power of 1 plus 0 times 2 to the power of 0, which is in fact equal to 2. So again, the way that the things get added in binary is that 1 plus 1 will give you 1, 0. But then if you want to translate everything back to decimal, you actually get the number 2, which makes sense. Okay, so now let's do a practice. So let's say now I have the number 1, 0, 1, and I want to add the number 1, 1 in binary, by the way. How do I do this? I'm going to give you guys again 30 seconds to attempt this, but remember, it's the exact same thing as decimal addition, with the exception that you get a carry bit once things add up to 2, or greater than 2 rather, instead of when things add up or become greater than 10. So take 30 seconds, think about this, and then we'll go through it together. Okay, so let's go through this together now. So I have here 1. I'm looking at this part right now. So I have 1 plus 1, and that is 2. And in binary, I get a 0 here. Oops, sorry, erase that. And then I get a carry bit of 1 over there on the next digit. And then on this digit now, and I'm going to space it off, I have 1 plus 0 plus 1. And again, this is, again, equal to 2. So I get a 0 here, and then I get another carry bit. And now in the next digit, I have 1 plus 1. And again, that's another 2, another carry bit, and then this final bit just carries down. And again, let's do the sanity check. Let's convert these to decimal and see if the numbers that we get actually make sense. So decimal. So 101 in decimal is 1 times 2 to the power of 2 plus 1 times 2 to the power of 0, which is just 5. Here, 1, 1, again, when I translate that to decimal, is 1 times 2 to the power of 1 plus 1 times 2 to the power of 0, which is 3. So when I add these two together, again, in the decimal land, I expect to get 8. Okay, and then what is the value of our output here? Well, I have 1 times 2 to the power of 3, and then plus nothing else because all the other bits are 0. And this is actually equal to 8. So we can see that, the sanity check makes sense. So when we do the binary addition this way, we end up getting the correct answer also when we translate things back to decimals. Okay, now let's talk about how to multiply bits. And again, binary multiplication is very similar to the multiplication that you guys are used to. So again, in here, 0 times 0 is 0. 0 times 1 is again equal to 0. 1 times 0 is again 0. And 1 times 1 is just 1. So this is something that, again, is almost identical to what you're used to in the decimal world, in the normal multiplication world. Now, again, we can, try to multiply two binary numbers the same way that we multiply two decimal numbers. So in this case, let's look at, 1, 1 times 1, 1. And, I'll give you 30 seconds, but again, just think of this as the same thing as normal multiplication that you're used to, with the exception of, when you're doing the addition down here somewhere, you get a carry bit once your numbers sum up to 2 or more instead of 10. Okay, so let's go through this together. So here I have a 1, and then I just multiplied by the numbers that I have up there. So I get, 1, 1, and then, okay, let's look at the next bit now. I put a 0 here, and then I have 1 times, 1 and 1. But pretty straightforward. So far, this is, identical to the way that you multiply, two numbers with more than one digit. Okay, now let me add these two numbers together, the 1, 1 and 1, 1, 0. Okay, so 1 plus 0 just gives me a 1. That was easy. Now, 1 plus 1 gives me a 2. So in binary land, I get a 0 here and a 1 that carries over. Now here I have 1 plus 1, which again gives me a 2. And then I get a carry bit over here. And okay, so let's again try to translate this to decimal to make sure to do our sanity check. So I have 1 times 2 to the power of 3 plus 1 times 2 to the power of 0, which gives me 9. And okay, this 1, 1 in binary is equal to 3 in decimal, and 3 times 3 is equal to 9. So we can see that, when we do this multiplication in decimal, it makes sense. It matches the multiplication that we do in binary. And again, this is how your computers do it. So computers think in terms of bits and binary, and this is how they, this is why they're able to do these operations the way that we just did. Now the question is why bits? Well, the main reason, the historical reason, is because bits, like having a system, having a variable that only has two possible values, like switch on and off or 0 and 1, is much easier to build hardware wise than if you have a system that has 10 possible values at every variable. And also something that we noticed here, I hope that you guys noticed, is that it's much faster to do binary operations than it is to do decimal operations. Because again, just based on some simple set of rules, like 4 set of rules, we're able to do everything real quick. And that actually translates very nicely for computers, the way that the computers think. So with that, let's take a 10-minute break until 3:15 Eastern Standard Time. And then we're going to talk about Boolean logics, or just gates, or you can think of them as operations. But yeah, anyways, I think we're going to take some questions now, if I'm not mistaken. But otherwise, I should, or rather, type your questions now. We'll go through them and then we'll answer them after the 10-minute break.
We will take a few questions and that you all have already sent. Gabby, do you have key questions you want to
Kira,
start us off with for Amir?
I'll jump in here, Kira. This is Rachel. Hi, everyone. There are a few questions just about summarizing key points. So Amir, can you just summarize what is binary and why is it important one more time so everyone really gets that key point?
Yeah, so binary is a way of representing a number which is in base of 2 instead of base 10 that we're used to. And the reason why it is important is because essentially it's the backbone and the building block of computers, both classical and even quantum in some sense. Now, we're not going to talk about the differences between a qubit and a classical bit in detail today, but at the end of the day, qubits are also operated in base 2. So after you measure your qubits, after your computation's done, you're either going to get 0 or 1. Now, what happens in the middle? That's quantum computing, and we're going to be talking about that in detail throughout the course. But the key takeaway is that, again, in binary, every digit has a value of 2 to the power of whatever that digit's position is, and that is the key difference between binary and decimal. And again, the reason why it is important to know binary is because normal computers are made out of bits. And every computation operation that we see is essentially a form of it's manipulating these bits to map some input into an output.
Great, thanks, Amir. And then I think there were several questions about topics we'll cover in the future. So complex numbers, vectors, but just to give folks a preview, can you tell us a little bit how you would represent non-integers?
Yeah, that's a good question. So if you guys remember, we represent non-integers in binary almost the same way that we represent 9 non-integer numbers in decimals. So for example, I guess I'm just going to write on this slide, right? If we have, we can have the number like, so we can have the number like 12.3 in decimal. Similar to that in the binary world, okay, actually, let me maybe write this down. So this is equal to, 1 times 10 to the 1 plus 2 times 10 to the 0. And now for this decimal is going to be equal to 3 times 10 to the power of -1. Now in binary, if you have a similar number, let's say, well, I mean, we can't have, 2 and 3, but let's say if I have, 1, 0.1, and again, this is, I'm going to call this decimal and this in binary, then that is equal to 2 times to the power of 1 plus 0 times to the power of 0. And now here, this 0.1 is 1 times 2 to the power of negative instead of 10 to the power. And again, the rest of the logic has the same flow.
Perfect. And then just to end the questions, can you possibly take us back and just walk through one of the multiplication examples one more time before we move ahead to make sure everyone really gets that?
Sure. Yeah. So maybe let's look at, again, this example of multiplication. So we kind of walk through, we approach this the same way that we approach, normal multiplication or decimal multiplication. So here, I have a 1 digit and I multiply this by the number above. So I get, 1, 1. And then here, I put a 0 down because I've moved the digit over. And then I do 1 times 1, 1, which again gives me 1, 1. So this part is identical to decimal multiplication. If anything, it's easier because your only possible numbers are 0 and 1. So it's like super fast to multiply. Now, the part that's going to be a little bit different is, when you add these two, right? Again, similar to normal decimal multiplication, you have to add, the top part plus the bottom part. And the trick is just in one fact that, again, in the decimal world, when your numbers add up to 10 or larger than 10, you have a carry bit, whereas like in binary, when they add up to 2 or larger than 2. So here I have 1 plus 0, and that gives me a 1. And then here I have 1 plus 1. So 1 plus 1 in a normal decimal world is 2, but 2 in binary is not allowed. So I get a 0 here, and I get a carry bit on the next digit. And then I have here 1 plus 1, which again is 2. So I get another 0 down here and another carry bit here, which gives me a 1. Now, we can do a sanity check on the side, convert everything to decimal, like, do the multiplication that we're used to, and just make sure that, like, the result that we get from our binary multiplication matches the result that we expect from decimal. And I mean, that is what we've done on the side. And we see that, like, for both cases, we get 9, whether we do it with binary or with decimal. And again, that goes just to the point of like the one point that I'm really trying to get across here is that anything that you can do or that we're doing with the decimal number system that we're used to, computers can also do with the binary numbers.
Perfect.
Any other questions, Rachel?
Nope, take us away.
Okay, amazing. So now we're going to get to the fun part of the course, which is talking about Boolean logic. So you might ask, what is Boolean logic? Boolean logic kind of might have a scary name even. So all it is that it maps input bits to output bits with some logic. So for example, and if something is a puppy and a kitten, it's the area of overlap in between them. If you want to show a picture. And I mean, you might ask yourself, why can something be a puppy and a kitten? And for those of us who were born in the 90s, we remember this cartoon called Cat Dog, which, there's a cat connected to a dog. The cat dog's both a puppy and a kitten. So if I look at the intersection of puppy and kitten, cat dog sits there. You can be like, okay, what is what are the set of things that are puppy or kitten? And that is almost all the cats and dogs in the world, plus cat dog.
Amir,
so, it needs to be either or.
Your microphone is going in and out a bit.
Oh, really?
A bit. Maybe it's going out 2 bits. Can you make sure that it's just adjusted? And if you can go over Boolean logic again, that would be great.
Yes, I can try. Okay, is this better now?
3 bits better.
3 bits, amazing. Okay, well, please let me know if it's having sound issues throughout the rest of the lecture. Okay, and then the last thing I want to talk about, again, just giving you guys a picture, we're going to be going into detail on these for the rest of our time. But, if we look at, the things like the combination of cats and dogs that are not kittens, it's just the set of puppies essentially, and that excludes cat dog because cat dog, is both a puppy and a kitten, and we want everything that's not a kitten. So this is how I can represent Boolean logic. We're going to talk about what logic gates are and what a truth table is. So a logic gate is essentially the bare bone operation that our computers do to for example, add and multiply things, or really, do any computation, as we'll see later. And a truth table, actually, let's start with a logic gate. So again, a logic gate, just maps, some input bits to some output bits. And, here are some examples. You don't have to take notes on the slide. We're going to go through each of these gates that are important one by one, and we'll go into detail. But just to give you guys an overview of what's to come, again, a logic gate is just something that maps and some input bits to some output bits based on some laws that we'll talk about. And a truth table, or as Kira likes to call it, a truth Hertz table, tells you what the output of these logic operations are based on the input. So for example, if we have a truth table that that looks like what we have on the left, what it tells us is that if this gate takes 2 inputs and both of the inputs are 0, we expect an output of 0. Whereas if both inputs are 1, we expect an output of 1. So again, all the truth table is what output do I get from this operation based on different inputs that I can feed it. And we will be seeing many examples of these truth tables throughout when we talk about logic gates, because essentially they're the roadmap of how a logic gate behaves. I'm gonna give you guys 10 seconds to appreciate this meme on the right side. Okay, we can move on. So let's talk about gates that only act on one bit. And the two gates here are NOT and fan out. So what is a NOT gate? The schematic of a NOT gate looks like what you see to the right here. So this is how we show a NOT gate schematically. And what it does is that it flips the bit. So if I input a 0, it outputs a 1. And if I output a 1, or sorry, if I input a 1, it outputs a 0. Okay, so I'm calling the input to this gate a variable a. Now let's write a truth table for this. So okay, input a, and then output. Okay, so I have one bit. So actually I'm just gonna call this a, so you don't have to deal with my handwriting. So if I only have one bit, the possible input values are going to be 0 and 1, because those are the only two values a single bit can have. Okay, so I told you guys that the NOT gate flips the bit. So if I input a 0, it will output a 1, and now if I input a 1, it'll output a 0. Simple as that. And this here is the truth table. And we will be using this truth table to talk about the behavior of all of our logic operations, or all of our gates. Okay, so this is NOT. The next option is fan out, which is just a fancy name for copy. So here again, the input is A. So if I input a 0, I expect to get 2 copies of 0. So I get 0, 0 in my output, two separate lines. Now, if I input a 1, I just expect to copy that 1. So I get 2 copies of 1. Simple. This is just, you take your bit and you copy it. So now again, if I'm trying to write a truth table for this, input A, output, we're going to see what the outputs are. I'm going to rewrite the outputs. So again, A is 1 bit, so it can either be 0 or 1. And if A is 0, then we'll get another copy of 0. So we get 2 zeros in output. And if A is a 1, we get 2 copies of 1 in the output. So we get 1, 1. Again, so the fan out gate just copies the bit. It's nothing too complicated. Okay. So these were the gates that acted on only 1 bit that I want to talk about. Now there are gates that act on 2 bits. And what we have here is AND, OR, or XOR. So let's see what these gates are. So the first gate I want to talk about here is AND. And what AND does is, again, so the AND gate looks, like this. If we were to schematically show it, I'm gonna, say that we have 2 input bits A and B, and the AND gate outputs a 1 if both A and B are 1, and it outputs a 0 otherwise. And actually, that's where the name comes from. It's like if A and B are both 1, then output a 1. Tell me if both A and B are 1. Okay, so if I were to write a truth table for this, so now I have 2 input bits, right? I have A, B, and then I have 1 output bit. Okay, so the possible values here are, I have 2 bits, so I can have both of them being 0, A being 0, B being 1, A being 1, B being 0, and then both A and B be 1. So based on the description that I just gave you guys, I want you to take, again, 30 seconds and try to fill this truth table for me. So tell me what the different outputs are based on these inputs. And again, just based on what we have up here in text.
Also, everyone, please don't ask questions in the Q&A chat until Amir either says we're on a break or that we can take questions then. We won't be able to go through all of the questions, and many of them are unrelated even to the course content that's occurring right now. So please make sure you're being respectful of that and focus just on the lecture. We promise you, as you keep going with this and in your lab this week and you review the material, do the homework, all of this will make a lot more sense if you're not getting it right off the bat. But a lot of these concepts go together from slide to slide. So you might not understand it on one slide, but you might understand it once it's put into context.
Yeah, thanks, Kira. So let's try to fill this truth table together now. So if both if A is 0 and B is 0, we get a 0 because both A and B aren't 0. Same if we have 0, 1, we also get 0. 1, 0, we also get 0. And it's only when both A and B are 1 that we get a 1 output. So this is the truth table for an AND gate. And if you guys look at this closely, this should remind you of, some like, normal arithmetic operation that, you might have seen. So the output here is actually A times B, or I can write it as A, times B. Because again, 0 times 0 is 0, 0 times 1 is 0, 1 times 1 is 0, and only 1 times 1 is equal to 1. And again, we'll see this, we will come back to this a little bit later. Okay, so I'm gonna give you guys a quick practice question, and I want you to tell me, if I have 1, 0 here, what do I get outputted, through my AND gate? And similarly, if I have, 1, 1 here, what do I get on this line? Again, this is how we show a logic operation. So you have, bit values on 2 different lines, and then, you basically want to see what is the value that comes on the output line. So, okay, if I have 1 and 0, we can either look at the truth table or just the definition. But the only way I get a 1 out of this gate is if both the bits are 1. So in this case, I get a 0, and here both the first bit and the second bit are 1, so I get a 1 out. Okay, let's move on to our next gate, which is OR. So the OR gate, which again looks something like this. You have the schematic to the top right of your screen. Outputs of 1 if either A or B is a 1, and outputs 0 if neither of the input bits, neither A nor B, are equal to 1. So with that, let's try to write a truth table for this again. Sorry. So I have 2 possible input values, or 2 possible input bits, A and B, and I want to see the output. So okay, A and B can be 0, 0, 0, 1, 1, 0, oops, sorry, 1, 0 I meant, and 1, 1. And again, take 20 seconds and try to fill this truth table by yourself, and then we'll go through it. Okay, so if A is 0 and B is equal to 0, neither are 1. So I expect an output of 0. But here, for the case of 0, 1, one of the bits is 1, so I get a 1. Again, 1, 0, again, one of the bits is 1, so I expect a 1. And 1, 1, at least one of the bits, but in this case, both the bits are 1, so I expect a 1 output. So this is what the truth table for the OR gate looks like. Now, again, let's do a quick practice. This is an OR gate. So what do you expect on this output line? Well, in this case, the top case, we have 0 and 1, so we have a 1 going in. So we expect the 1 output.
Amir, your microphone is going in and out again.
Okay. Weird. Is it?
No.
Okay, how about now? Is this better?
Yes.
Okay, so this is a different microphone that I'm using now. Let's hope it's still good. Okay, let's continue. And then here we have 1, 1. So both of our bits are 1. And then based on the truth table, we expect another 1 on the output. And finally, let's talk about XOR, which actually is an, I'm going to write this up here, is an exclusive OR gate. So again, the schematic is what we have on the top right. And this gate outputs a 1 if either A or B is 1, but not both. So the gate will output a 0 if neither A or B is 1, or both A and B are 1. And how can I show this? Okay, well, again, let's go to the truth table. And hopefully by now, you guys have gone more experienced. So I'm going to actually have you write down the truth table from scratch. And remember, we have different inputs and different outputs. And I want you to write a truth table from scratch. And let's take, again, 30 seconds for this, and then I will write down the truth table myself. Okay, so I'm going to start setting up the truth table now. So we have 2 input bits, A and B, and an output bit. So, again, the possible values are 0, 0, 0, 1, 1, 0, and 1, 1. Okay, so we said if neither A or B are 1, so if both A and B are 0, then we expect a 0 on the output. If one of them is 1, but not both, we expect a 1. And then if both are 1, we expect a 0. So this is what the truth table looks like for XOR. And again, let's just do a quick practice. So show XOR like this. If I have 1, 0, and again, let's just look at 1, 1. So here again, well, we have a 1 and a 0, so we expect a 1 on the output. And here we have 2 1s, so we expect a 0 on the output. Now, another way of showing XOR, by the way, like if I want to write A, actually that's on the beautiful X. If I want A, X, or B, I can also write that as A, and then this circle plus sign, B. That is another way of showing XOR. And we will see, why we want to write things down this way momentarily. Okay, so the concept that I want to talk to you guys about now is universality. And what the important takeaway message from universality is that any computation operation can be made using a combination of not, and, or, and fan out, or I'm just going to write copy under. And let's just take a moment to think about this statement. This is a very powerful statement. So what I'm telling you guys here is, these 4, fairly simple logical operation that we talked about are, what makes every computer essentially work. So, when you send a text to your friend, when you check your Facebook, when you, log on to Zoom, when you post something on TikTok, all of that, everything your computer does can be boiled down to a combination of, these 4 operations. And that's mind-blowing. Like, I remember when I learned about this just sounded insane to me. Like that, 4 seemingly simple, logical gates that we talked about are the basis for everything that our computers can do. And that is the concept of universality. So let's see that in action. I'm going to introduce another gate, which is, a NAND or a not AND gate, which, can be made using a combination of an AND gate and a NOT gate. And then we're going to see, what this gate does based on this combination. So what I want you guys to do, again, probably from your notes, but if you could write the truth table for AND and NOT, we're going to see if we can figure out the truth table for this NAND, which is, first, if we have A and B, we apply an AND to A and B, we get an output C, and then we apply a NOT to this output C. So again, I want you to give you guys 30 seconds, write down the truth table for AND and NOT first, and then we'll take the next step. Okay, so I can go ahead and start writing. For AND, we have ABC and output. I'm just going to write it as out. So possible inputs are 0, 0, 0, 1, 1, 0, and 1, 1. And for an AND, we get zeros, except for when both A and B are 1. Or I guess in this case, actually, the output, I just called it C. So let me just replace that with C. And here for the NOT, if my input is C, the possible values can either be 0 or 1, and it's a NOT gate, so it just flips a bit. So if I input a 0, I get a 1, and if I input a 1, I get a 0. So based on this, what do I expect for NAND? Well, okay, let me set up the truth table, and I'm going to ask if you guys could complete it. So, okay, I said that my inputs are A and B. I'm just going to call, the output out. Again, possible inputs are 0, 0, 0, 1, 1, 0, and 1, 1. So take another 30 seconds to think about the output, and then I will write it down for you guys. And again, remember that, a NAND is a combination of not and an and.
I also want to remind everyone that these, if you're getting confused on the various symbols and how to, memorize them, Amir, if you have any techniques, that's great. Another thing, you can just make flashcards for these few different gates, and really so you can understand them. Once you do understand and remember the difference between them, it becomes a lot easier. Again, it's not something that you're expected to pick up right away, but by the time that you go through your next lab, and you'll cover these again, you should feel, a lot better about knowing these. This is still really new, so just do as well as you can right now.
And to echo Kira's point, when I learned about logical operations, I did not remember what the exact symbols were immediately. What you should really try to get out of this lecture at least is, first of all, understand what these operations are doing. So when I tell you, like, I'm interested in an AND operation, you should know, what does an AND do, and also be able to write a truth table down for it. And once you have these two skills, you can essentially build anything on top of that. And these symbols are something that, like, with exposure, you will remember. I mean, I know them pretty well by now, but again, when I started, it definitely took me a while to, like, be able to exactly map, what the AND symbol is to, like, oh, this is an AND gate. But don't worry about that part too much. Okay, so let's go through this. Let's try to populate the truth table now. So, okay, if we have 0, 0 as an input, the output of the AND gate, the first part, is a 0. And then when this 0 goes through the NOT gate, it becomes a 1. So I get a 1 here. And actually, it's very similar for 0, 1 and 1, 0 as well. So when 0, 1 and 1, 0 go through this AND gate, I get an output of 0 from the AND. And then when that 0 goes through the NOT gate, I get a 1. So here I get 1 and a 1. Now, if my input to the NAND gate is 1, 1, the AND part, takes this 1, 1 and outputs another 1. So the C value would be 1. And then this 1 goes through the NOT gate. And again, here the 1 gets mapped to a 0. So this is how we can write the truth table of a NAND gate. And again, all it is, like, now that we have the truth table, let's try to put it in words. Let's try to describe what this gate does, this NAND gate that we constructed by combining an AND and a NOT. So it outputs a 0 if both A and B are 1, and it outputs a 1 if otherwise. So again, nothing, like, it's just combining, the things we've seen so far. Okay, so here's a pretty cool exercise that I want us to do together. And so we talked about these, logical operations, but these are not things that we're used to dealing with on a daily basis. Now the question is, and I made the claim that, that the operations that we talked about are universal, meaning that you can, do any computing process by combining these. So now what I'm going to ask you guys to do is, or, we're going to do together, is let's make a binary adder with the gates that we have. And a binary adder takes 2 bits. In this case, we won't going to make it for 2 bits, and adds the bits together. So let's first begin by writing a truth table for this binary adder. So, what is the objective? I'm trying to do A plus B. Okay, so I have 2 possible inputs, again, A and B, and an output that's going to have 2 bits, actually. and we're going to see why. I'm going to draw a dotted line here. Okay, so, well, A and B can be, again, 0, 0, 0, 1, 1, 0, and 1, 1, correct? Okay, so, I mean, this part is just simple addition, and this is something that we've seen earlier in lecture. So 0 plus 0 gives me a 0. 0 plus 1 gives me a 1. 1 plus 0 gives me a 1. And 1 plus 1, again, gives me a 2 in decimal, which I can write as 1, 0 in binary. And actually, that was the reason why I drew this dotted line here, in a sense, because the output, like in order to represent the output of summation, we need 2 bits instead of just 1. Because the 1, 1, the output of that is a 2-bit number. So I'm just gonna for the ones that don't have a 1 on this left bit on the output, I'm just gonna put down zeros. So again, I have 0, 0, which is just 0, 0, 1, which is 1 for the output. Number 0, 1, which is a 1, and then 1, 0, which is 2 in binary. Okay, so this is the truth table for our adder. Now, let's think about this a little bit. I kind of want to break this down to 2 parts deliberately. So I'm going to call this, we're going to look at, a truth table, like what is the rightmost bit of the output based on A and B, and the leftmost bit of the output based on A and B. So I'm going to call this, bit 0 and bit 1. Oops. Okay, again, truth table with A and B, 0, 0, 0, 1, 1, 0, and 1, 1. So let's look at, bit 0 that I have designated bit 0 of the output. So I'm just copy and pasting this column over here. The possible values are 0, 1, 1, 0. And then I'm going to, redo this whole thing again for bit 1, or the left bit of the output. So A, B, and bit 1. Now your possible input values are 0, 0, 0, 1, 1, 0, and 1, 1. And here, I'm just copy and pasting this column. So 0, 0, 0, 1. Okay, so I want you guys to take, 20 seconds or 30 seconds, look through your notes and tell me, or, I guess I don't have any way of directly communicating with you, but, guess, which operation has the same truth table, which one of the operations that we've talked about has the same truth table as either one of these. Okay, so I'm going to start with bit 1. So when I look at this, I'm getting zeros for all inputs except for when both inputs are 1. And that reminds me of an AND gate, which I'm going to represent as A dot B, doesn't matter, but here's an AND. Okay, what about bit 0? Well, so I'm getting zeros when both A and B are 0, or when both A and B are 1. So this reminds me of the XOR gate that we talked about. Okay, so the moral of the story is that if I combine these 2 gates, I can make a binary adder. So let's see how that looks like. So again, let's say I'm trying to add, 2 bits A and B. First thing I need to do is that I need to make a copy of A and B, or, use a fan out. So, okay, here's a copy of my A. The copy of my A, and here's a copy of my B, And okay, to make bit 0, which I'm going to call this, whatever comes this bottom, out of this bottom part, bit 0, I need to apply an XOR to A and B. And then this is how I get bit 0. And to get bit 1, I need to apply an AND to A and B. So this is bit 1. And something that I want to leave to you guys as an exercise for after the after this lecture is, so again, just go through this, go through what we have here as a binary adder, and convince yourself, if you're not already convinced, that this actually takes two 1-bit binary numbers and adds them together. Okay, with that, we're almost coming to the end. I want to talk about the concept of reversibility now. And what reversibility means is, if I give you the output of a gate, can you tell me what the inputs are for sure? Let's look at 2 examples. So I'm going to ask you, is not reversible. And the way that we can assess this is, okay, if the output is a 1 of a NOT gate, can you tell me what the input is? Well, yes, we know that if the output is 1, then the input has to be a 0, because NOT gate flips a bit. And similarly, if the output is 0, then the input has to be a 1. So okay, for NOT, I can tell you what the inputs were based on what the output values are. So that means that NOT is reversible indeed. Okay, what about the AND gate? So let's say I tell you that an AND gate has an output of 1. Well, we know that an AND gate only inputs a 1 when both the input bits are also 1. So then you can tell me, yeah, okay, the inputs need to be 1, 1. Perfect. Now, if I tell you that the output, actually 1, 1, 1 and 1, if the input is a 0, well, what then? So this gets a little tricky, right? Because if the output is 0, because the inputs can be 0, 0, that gives me a 0. It can be a 1, 0, because that also gives me as, oops, let's erase this real quick. 1, 0, because that also gives me an output of 0, and it can also be 0, 1, because that also gives me an output of 0. So an AND gate is not reversible, because I can't tell exactly what the outputs are or what the inputs are based on the output. So for that, a reversible gate is a gate that preserves all the information, again, because I can back solve what the inputs are or where based on the outputs that I have at hand. And a non-reversible gate loses some information. Now, in normal computing, in classical computing, it doesn't matter if a gate is reversible or non-reversible, but in quantum computing, all your gates have to be reversible. And the reason for that is actually, information has a physical meaning. And, the laws of physics penalize you if you lose information. And, that penalty usually comes in the form of energy dissipation and heating. Now, classical computers, a classical bit is not that fragile that, this loss of information will affect it that much. Whereas in quantum computing, if you end up losing information, this energy dissipation that you get will destroy your computation and your quantum state. So to end the lecture, I just want to emphasize that for quantum computers, all of your operations, all these quantum gates have to be reversible. And again, this is something that we'll see and we'll emphasize throughout the course. But yeah, on that end, I guess on that note, I want to end the lecture. I think I'm going to pass it to Kira now to tell us what else is happening this week.
Awesome. So just quickly, Amir, could you go over what the lecture is going to cover next week? And then I'll go through just some of these logistics. So everyone hang tight for an extra minute or two.
Oh, absolutely. Yeah, sorry. So the lecture next week is going to cover quantum computing in abstract. So while to fully understand quantum computing, you need some math background, which is what we're going to be doing for the rest of this semester. It's cool to see what are some cool topics of quantum computing. We're going to have a sneak peek for the second semester of the course. So that's what we're going to be talking about. Essentially, it's going to be quantum computing with almost no math and just a cool concepts.
Awesome. Thanks so much, Amir. So we're really, again, so excited. I've been pumped listening through all of this. We've been spending a ton of time going over the content, making sure it's as accessible as possible. But I'm going to be completely frank with you. The first time Amir showed me this lecture, I was so confused. I did not understand how to convert binary to decimals or vice versa. I didn't get the point of gates or truth tables. So, it takes a bit of time. I went through this lecture and thought, oh my gosh, I actually understand all of this. So one, know that there are people on our side going through this as well. And as what I say is extremely genuine in terms of this just takes a bit of time to truly understand. And for those of you who are already more advanced and understand this, again, don't worry, there will be more advanced material coming. But first, to get everyone on the same page, it's really important that we solidify the basics. So just to go over some announcements, labs, like I said, are going to start this week. If you haven't received an email yet about them because you confirmed your spot yesterday or today, you will receive an email about it. Second, there will be homework. This is a great time for you to practice through and work through some of these problems. It will be available on Discord after the lecture finishes. So definitely check the course announcements. Also, I believe Gabby will be posting it here as well. Again, as it says, you will not be submitting this to Canvas this week. So make sure you write down your answers somewhere. Next week, when we open up Canvas, you will be submitting this homework assignment. So just be clear on that. Just a few other important notes. Make sure by the end of the day tomorrow, you sign up for your lab time. It is critical that you do this as soon as possible. If you have not done so already, confirm your acceptance. We need this to know how many students are actually in the course. A number of you have signed up for labs without actually confirming your spot. Make sure you're on Discord. That is going to be where we communicate everything. And we will be sending out information about Piazza starting later today, but we'll be doing this through Tuesday. This again, if you are confused or you have questions, this is where you would post them about anything related to the content that was covered today. For right now, please don't post questions outside of the scope of what was covered in the content. We promise we will be opening up channels where you can post other things and possibly TAs will answer them. But for right now, it's really important that we get everyone on the same page so we can all move forward together. Amir, if you want to switch to the next slide. And once again, since many of you are joining us today, we have a ton of available options to follow us on various social media platforms. We would love for you to do so. We'll be highlighting students like yourself throughout the semester and offering, other cool content on these sites. So would love for you to follow us. Again, we are so incredibly excited for you all to be in this course, and we can't wait to get started. So thank you again. And Amir, you can just go to the last slide as we finish out. Thank you so much, and we will see you all in your labs this week. And Amir, you can actually go back to the last slide if you want. And so I've gained you some messages about people wanting to see our handle. Thanks. Awesome. Thanks everyone so much again.